Welcome back to the Deep Dive, where we sift through the latest insights and try to uncover the really fascinating nuggets of knowledge just for you. Today, we're plunging into the world of abstract analysis. That's, pure mathematics. We're going to unpack a pretty groundbreaking piece of research that's definitely sending ripples through the field. Ever wondered what it takes to, overturn a long-standing belief in high-level mathematics? That's basically our mission today. We're diving deep into a paper from February 2025 by Cairo. It's titled, A Counterexample to the Mizohata-Takeuchi Conjecture. And yeah, it's a definitive gotcha moment. It's really reshaped how mathematicians are viewing certain problems.
It's actually quite remarkable how a single incredibly clever construction can just, completely upend an entire field's understanding. So this deep dive will guide you through what the Mizohata-Takeuchi conjecture was, why it held such significance, and then crucially how Cairo's work definitively showed it to be false, which charts completely new paths for future mathematical exploration.
Okay, let's unpack this then. Before we get to the big reveal, what exactly is the Mizohata-Takeuchi conjecture? Conjecture 1.1, right? It sounds kind of intense.
Yeah, it does sound a bit sci-fi maybe, but at its heart, this conjecture is about understanding how functions behave. Specifically, when you extend them from some kind of curved surface into the space around them. So imagine you have a function, let's call it f. It's defined on a curved surfacing like the skin of a balloon or maybe a potato chip, something not flat. Then there's this thing called the extension operator, usually shown as the symbol arrow, and it essentially projects or transforms this function from that surface out into the full three-dimensional space.
Okay, like how a sound wave might spread out.
Exactly. That's a great analogy, like a sound wave starting on the balloon's surface and then spreading outwards into the room. So the conjecture then proposed a very specific inequality, a mathematical relationship. It suggested that if you looked at the, let's call it the energy or intensity of this extended function out in 3D space, and you weighted it by another function, let's call that WA, then that total energy would always be bounded. It wouldn't blow up. More precisely, it claimed this weighted energy would be less than or equal to the original function's energy back on the surface, multiplied by something called the X-ray transform of that weight function W.
The X-ray transform. Okay, are we talking about actual hospital X-rays here? Or?
Hey, no, not medical X-rays. Good question, though. The concept is related in a way. The X-ray transform XW for a given weight W, it's simply a measure of that weight's mass or intensity, but integrated along every possible straight line going through space.
Ah, okay. So if W is like density, XW tells you how much stuff a beam would hit.
You got it. That's the idea. So the conjecture was essentially saying the spread of our extended function degree is controlled. It's controlled by how strong F was initially on the surface and by how concentrated that weight W is along any straight path.
Right. So, okay, this still sounds pretty abstract, a math problem about functions and weights. Why should you, our listener, really care about this specific inequality? What made it such a cornerstone?
That's an excellent question and really important because while it is abstract, this conjecture had surprisingly deep, almost practical connections. These connections made it a critical puzzle piece in harmonic analysis, which is a branch of math that helps us understand complex signals, waves, that kind of thing.
Right.
For one thing, its roots actually go back to physics.
Yeah.
It first popped up in the late 1970s, early 80s. A mathematician named Takeuchi was studying something called the well-posedness of the Schrödinger equation.
The Schrödinger equation, that's quantum mechanics, right? Describing particles.
Exactly, fundamental stuff. And well-posedness is basically asking if the solutions to an equation are, well-behaved. Do they exist? Are they unique? Do they not suddenly explode or just vanish? Which is, pretty crucial if you want to predict anything physical. Takeuchi believed this conjecture offered a sufficient condition for those quantum solutions to be stable. Mizohata later found an issue in Takeuchi's specific argument, but the basic link was there. This abstract math problem seemed connected to understanding quantum systems.
Wow, okay, so a direct link to quantum physics. That definitely raises the stakes beyond just pure math. What else made it so important?
Well, another huge reason was its potential impact on other big mathematical challenges. In 2006, another major conjecture was formulated, the multilinear restriction conjecture, or conjecture 1.3. Think of it as a much more complicated version of our problem, dealing with several functions and surfaces all interacting. Very tricky stuff. And recent work by CHV, that's Carberry, Hebish, and Valdimarsson in 2018 and 2023, they showed that if Mizohata-Takeuchi was true, then it would directly imply this big multilinear restriction conjecture. And it would imply it without a certain type of error or inefficiency in the mathematical bound, these things called re-losses.
Or epsilon losses, like a small fudge factor you want to get rid of.
Kind of, yeah. Getting rid of those losses would have been a massive theoretical leap. It would have simplified a really difficult area and opened doors for other proofs.
So proving Mizohata-Takeuchi was seen as a shortcut, almost?
In a way. And then there's its relationship to Stein's conjecture. Back in 1978, Elias Stein, another really influential mathematician, proposed an even stronger related conjecture, conjecture 1.4. Now, if Stein's conjecture were true, it would automatically imply Mizohata-Takeuchi.
Ah, okay, so MT was like a stepping stone towards an even bigger prize.
Precisely. So proving it felt like progress towards this grander goal in the field.
So it really was like a master key, potentially unlocking these other major mathematical doors.
Exactly. And, beyond these direct implications, the conjecture had this unique intrinsic value, too. Most research in this area, it focuses on how operators map functions between spaces, sort of algebraically. But this conjecture, Mizohata-Takeuchi, was one of the few attempts trying to understand the actual geometric shape of the regions where the extended function degree had certain values. It gave a kind of visual perspective.
So it helped mathematicians sort of see these abstract things.
Right, which not many other approaches were doing. So its disproof was particularly impactful for how people visualize these concepts. It's kind of bittersweet for the field, Years of effort down one path, finding it's a dead end. But that dead end also forces you to look for completely new, maybe unexpected routes.
Okay, this is where it gets really interesting then. Decades pass. Researchers are working on this, making some progress. You mentioned people like Barcelo, Ruiz, Vega proved special cases. Others showed it held with some loss, but not without. But then, February 2025, Hannah Cairo publishes her paper. What was the big discovery?
The discovery was, definitive. The Mizohata-Takeuchi conjecture, exactly as it was stated, it's false. She constructed a very specific mathematical scenario, what we call a counterexample, where that inequality just does not hold true. It fails.
Wow. So it's just wrong. How does that happen? How can a math conjecture just be wrong? Doesn't math always have, a right answer?
That's a great question. And it gets at the heart of how math research works. See, a conjecture is a statement that's believed to be true, based on evidence, but it hasn't been rigorously proven yet. To prove it false, you just need to find one single instance where it doesn't work. That's enough. And Cairo found one. She found a specific function, f, and a specific weight, w, for a particular kind of surface, a smoothly curving one, but definitely not flat, like a gentle hill, where the left side of that inequality, the energy side, is actually larger than the right side, the X-ray transform side.
Larger, so the bound just didn't hold.
Right. And here's the kicker. It's not just larger by some fixed amount. It's larger by a factor that grows as you change a parameter, r. It grows logarithmically with r.
A log r loss. Okay, what does that mean for us in plain English? Break that down.
It means the proposed bound isn't just a little bit off sometimes. It's fundamentally insufficient. As r, which you can think of as related to the scale or the size of the region you're looking at, gets bigger and bigger, the inequality fails more and more dramatically. Imagine the conjecture said, this thing x is always less than 100. Cairo found cases where x is less than 100 times the logarithm of r, and the logarithm of r, log r, can become arbitrarily large as r grows.
Oh, okay. So it's not just failing, it's failing worse and worse as you scale things up.
Exactly. It definitively closes the door on the original conjecture. The proposed bound was just too optimistic.
This is fascinating. But okay, how do you do that? How do you actually build a counterexample to such a foundational idea,
right,
especially with this kind of abstract math? So let's try and get the how in a way we can grasp.
Right. It's a really clever mix. It involves building very specific sort of custom designed functions and then relying on some pretty intricate geometry. Think of it like designing a highly precise trap, specifically engineered to catch the conjecture in a moment where it breaks down.
Okay, a trap. I like that.
So first, Cairo built on existing theory. She derived some really precise estimates for the X-ray transform, but for something called positive measures. This is Theorem 2.1 in the paper. This was a key foundational step because it let her translate the abstract X-ray transform, which is hard to work with directly, into more manageable functions, things she could actually construct and control.
So she found a way to sort of decode the difficult part.
In essence, yes,
Yeah.
to make it easier to handle. And then came this idea of the white lie proof.
The white lie proof. I love that term. So what's the gist? Give us the simplified version.
Okay, so the white lie proof, it's less rigorous, maybe cuts a few corners technically, but it gives you the core intuition really clearly without getting bogged down initially. So imagine our smoothly curving surface, again, the potato chip. She picks a number of points on it, say n points, and this number n, it grows, but slowly, in proportion to log r. Think of these endpoints as tiny beacons or hotspots scattered on the surface.
Okay, n beacons growing with log r. Got it.
Then she defines her function f, and f basically just lights up those beacon points. It's concentrated right there. Next, she creates this special arrangement of points out in the full 3D space. She calls it a lattice queue. This lattice is built using specific combinations, sums of those n beacon points from the surface. And the size of this lattice, the number of points in Q, it explodes as n increases. It grows exponentially fast, like really fast.
Wow, okay, so a huge, intricate network of points based on the beacons.
Exactly, a vast network. And finally, she constructs the crucial function h. This h is directly related to the weight w that's going to break the conjecture. And h is defined basically as a collection of tiny, tiny balls. Each ball has a very small radius, like rho, really small.
Right.
And there's one ball centered at every single point in that massive lattice queue.
So like a giant constellation of tiny spheres.
Kind of, yeah. And the white lie part was making a helpful approximation about the sort of frequency content, the Fourier transform, of this function h. They assumed it was contained in a nice, manageable region. So the ingenious part was then comparing the two sides of the original Mizohata-Takeuchi inequality, using this specific f and this specific h related to w. When she did the calculation, roughly speaking, the left side of the inequality, the energy part, it grew like n times the size of the lattice Q.
Yeah.
But the part with the X-ray transform, it grew more like just Q, assuming a key geometric property held.
Oh. And since n grows like log r, that n on the left side becomes like log r. Wait, you said log r loss before?
Right, sorry. The simplified white lie gives something like log r. The actual rigorous proof refines it down to the log r loss. But the core idea is the same. The left side grows faster than the right side because of that n factor, which depends on log r. That's where the failure comes from.
Okay. So the white lie shows why it fails, gives the intuition. But then you need the rigorous part. What was the really hard bit to make it mathematically airtight? The non-white lie.
The most challenging part, was rigorously proving a specific geometric result. It's called the incidence geometry lemma. In the paper Lemma 3.5, which itself relies heavily on another result, Lemma 4.1, this lemma is absolutely critical. It's the mathematical guarantee that the geometric assumption used in the white lie about the X-ray transform was actually valid.
What did it guarantee exactly?
Specifically, it ensured that even with all those countless tiny balls making up a space spread out according to that huge lattice Q, no single flat plane anywhere in 3D space could pass through too many of the centers of those balls simultaneously.
Okay, so it limits how much those balls can line up on any flat slice.
Precisely. This is what kept the maximum value, the Euler norm of the X-ray transform, XW, bounded by just a constant. If XW had also grown large, it might have canceled out the log R factor on the other side. But because this lemma kept XW under control, that log R loss emerged as the dominant inescapable factor causing the inequality to fail.
And how on earth do you prove something like that? Guaranteeing no plane hits too many points in this massive complex lattice sounds incredibly intricate.
It is intricate, but the technique is quite elegant. It relies on something called induction on dimension. They used a specific curve, the moment curve, which is defined like T2ST as a kind of model for these curved surfaces. This moment curve has really nice properties. It behaves well under scaling and interacts nicely with a certain projection map that essentially lets them reduce a problem in, say, D dimensions down to a similar but simpler problem in D1 dimensions.
So they break it down, like simplifying the problem layer by layer.
Exactly. It's like taking a massive, complex jigsaw puzzle and breaking it down into a series of smaller, slightly easier versions of the puzzle until you get to one you can actually solve easily. That reduction is key.
Wow. Okay, so the paper doesn't just disprove the conjecture, it really changes the landscape. What are the immediate knock-on effects? What happens now in the field?
You're absolutely right. It has significant consequences. First, for those multilinear restriction estimates we talked about, that direct path to proving conjecture 1.3 without those ray losses, the one that relied on Mizohata-Takeuchi being true, that path is now definitively closed. Researchers like CHV who are pioneering that approach, they'll need to find entirely new strategies now to try and sharpen those estimates. Back to the drawing board in some ways.
Okay, so that door is shut. What about Stein's conjecture, the stronger one?
Right. Since Stein's conjecture, conjecture 1.4, implies Mizohata-Takeuchi, Cairo's counterexample automatically means Stein's conjecture is also false, as it was originally stated. However, the counterexample here only shows the failure up to this logarithmic factor, this log R loss. That actually leaves some fascinating room. It means a slightly weaker, maybe local version of Stein's conjecture might still hold true. It's not a complete demolition, but a significant refinement of what might be possible.
Interesting. So it narrows the possibilities. And what about the physics connection, the Schrödinger equation?
Yeah, for anyone working on the well-posedness of certain types of Schrödinger equations, specifically first-order perturbations, any arguments they had that explicitly relied on the original Mizohata-Takeuchi conjecture holding true, those arguments now need careful reevaluation. It doesn't automatically mean the physical solutions aren't well behaved, but the specific mathematical justification used might no longer be valid. They might need a new proof.
So, quite a ripple effect then. If the original conjecture is busted, what's next? Do mathematicians just, give up on this line of inquiry?
Oh, not at all. This is where science really progresses, right? By understanding the limitations. Cairo's paper doesn't just tear down, it also proposes a way forward. She suggests a local Mizohata-Takeuchi conjecture, conjecture 1.5. This new reformulated conjecture basically acknowledges, okay, the original was too strong, there has to be some loss. It specifically suggests maybe an error loss is needed where that epsilon can be arbitrarily small, but it's still positive.
So, trying to find the right weakened version that might actually be true.
Exactly. It's a common and really productive thing in math. If something's too strong, you refine it, find the true boundary of what's possible. And the big question now is even this local ray version true? Or is there maybe an even larger, more fundamental loss needed? There's earlier work by Guth on something called decoupling axioms, which might suggest a larger loss, like r raised to the power of n1, n plus 1. So the journey continues. Understanding the limits is just as important as proving what is possible, even if a major landmark turned out to be, well, a bit of a mirage.
What an incredible deep dive, seriously. From these really abstract equations to a concrete, definitive disproof. It's just a powerful reminder that even in mathematics, these definitive answers can still surprise us and really open up entirely new ways of thinking and the human ingenuity involved, to construct something so specific, to prove an idea wrong with such elegance. That's really inspiring.
Absolutely. This paper, it doesn't just solve a long-standing problem. It leaves us with genuinely new, fascinating questions. Questions about the fundamental limits of these mathematical estimates and the true shape, the true geometry of these abstract objects. It forces the field to dig deeper into that subtle interplay between the geometry of surfaces and the analysis of functions. It's a moment of clarity, really, that will definitely shape research for years to come.
Well, that's all the time we have for this deep dive. We really hope you feel a little more informed and maybe a lot more curious about the hidden structures underpinning, well, everything. Until next time, keep digging into what fascinates you.
欢迎收听豆包 AI 播客节目。
Hello， 大家好，欢迎收听我们这一期播客啊。然后今天咱们来聊一聊啊，关于数学当中的一些问题啊。我们今天特别要聊的是 Mizohata-Takeuchi 猜想，以及和这个猜想相关的一些研究啊，包括一些反例啊，一些这个 X 射线变换的估计啊，包括这个猜想和其他的一些数学领域之间的联系啊。那
感觉很有意思。那我们就赶紧开始吧，一起来探索一下这些数学背后的故事。
首先啊，咱们今天要聊的第一个问题是，这篇论文到底干了些什么？
这篇论文呢，它主要就是做了两件事情。第一件事情就是它推导出了在 2D 上面的正测度的 X 射线变换的 LP 估计。然后第二件事情呢，就是它利用这个估计构造了一个 log R loss 的反例，来否定了 Mizohata-Takeuchi 猜想对于任意的不包含在超平面内的 C2 维超曲面。
哇，听起来好厉害啊！就是尤其是这个构造反例来否定这个猜想，这个听起来就很让人兴奋啊。
对，而且他这个还顺便得到了一个结论，就是说 Mizohata-Takeuchi 猜想没有办法直接去 sharpen 这个 endpoint 的 multilinear restriction estimates。对，然后这篇文章的结构呢，就是它首先是有一个 introduction， 就是介绍了一下这些背景。在第二部分呢，它就推导了这个 X 射线变换的估计。在第三部分呢，它就构造了这个反例，最后是一个 appendix， 就是补充了一些计算的细节。
哦，那就是说这个 Mizohata-Takeuchi 猜想它到底是一个什么样的东西啊？然后它为什么会这么重要呢？它是怎么跟其他的这些重要的数学问题联系起来的呢？
这个猜想呢，它其实是一开始的时候是出现在研究这个 dispersive PDE 的 well-posedness， 对，然后后来呢，它就变成了 Fourier restriction theory 里面的一个核心问题。它甚至就是跟 Stein 猜想和 Kakia-Maximo 猜想都有很深刻的联系，它也可以推出 multilinear restriction estimates。
哇，听起来它真的是一个好多领域的一个桥梁啊。
对，但是很可惜，就是这篇文章的这个反例就说明，就是 Mizohata-Takeuchi 猜想是不成立的，然后包括 Stein 猜想也是不成立的。但是如果假设 Kakia-Maximo 猜想成立的话，那么 Stein 猜想的一个局部的版本还是可以推出 restriction conjecture。 对，这个也说明就是这些猜想之间的关系其实要比想象的更微妙。
那就是说这个 Mizohata-Takeuchi 猜想它的研究现状是什么样的？就是它现在有哪些进展，然后有哪些可能的未来的方向呢？
这个问题呢，就是有很多数学家都研究过，比如说 Barcelo、Ruiz 和 Vega 他们就解决了这个 radial 的 case。然后还有比如说 Xiaol， 他就是在研究这个 conjecture 和这个测度的 Fourier transform 的 decay 之间的联系。包括最近的 Ortiz， 他就是对于这个 cone 证明了这个 conjecture， 但是有一个 r 的1/4次方加 epsilon 的损失。
哇，听起来这些进展都真的很厉害啊。
对，然后包括还有一些更精细的结果，比如说 Carberry、Eliopol 和 Wang， 他们就是对于更广泛的一类 weight证明了这个 conjecture， 但是有一个 r 的 n+1/n-1 次方加 epsilon 的损失。对，甚至 Goff 还证明了，就是如果你只用特定的 decoupling 的方法的话，那么你是没有办法突破这个损失的。对，所以就是说这个问题现在就是说大家可能会去研究的一个方向，就是去看这个 local 的 conjecture， 或者说去研究一些 weaker 的 inequality。
那就是说这个关于这个 X 射线变换对于正测度的估计，这篇文章里面主要得到了什么样的结果呢？
它就是证明了一个就是对于weight W 和 function h 之间的一个不等式。然后这个不等式呢，它是涉及到了X 射线变换的 LP 范数和这个 P new H 的 LQ 范数之间的一个关系。它甚至还证明了，就是这个等号成立的条件是当且仅当 H 是非负的，并且 P 等于无穷的时候。
哇，听起来好厉害啊！就是尤其是这个等号成立的条件，这个很让人意外啊。
对，然后它这个证明呢，就是主要是用到了这个 projection slice 定理，还有 Minkowski 不等式和 Hausdorff-Young 不等式。它这个等号成立的这个 sharpness， 它也特别说明了，是因为这几个不等式的等号成立条件是可以同时满足的。
那就是说这个文章里面是怎么来完成这个 theorem 1.2的证明的呢？
它就是先把这个问题转化成了一个关于二次形的问题，就是它定义了一个 EWFG 这样的一个东西，然后它把它看成是 L2 sigma 上面的一个 quadratic form。他说就是这个 Mizohata-Takeuchi 猜想其实就是在问这个 quadratic form 的最大的一纲例头是不是有一个用 XW 的 L 无穷范数来控制的一个上界。
哇，听起来好厉害啊！就是尤其是这个转化，这个很让人意外啊。
对，然后他就是通过一系列的推导，把这个问题最终化约到了去证明一个关于 H 和 F 的一个卷积的 L2 范数的一个估计。他也提出了一个稍微弱一点的 conjecture， 就是说他把这个问题局部化了之后的一个猜想。
哇，今天我们真的聊了好多啊，从这个 Mizohata-Takeuchi 猜想的起源啊，到它的这个与其他领域的深刻的联系啊，然后再到这个反例的构造以及一些相关的估计啊，真的是感觉让人目不暇接啊，真的是一个非常充满了挑战和惊喜的一个领域啊。
OK 了，以上就是这期播客的全部内容了，感谢大家的收听，咱们下期再见，拜拜。